To predict the products of these alcohol reactions, I have two systems on here that may not be familiar, and they're added on for those students who may need these things moving forward or perhaps who are going towards the MCAT. And we're going to start with PCC, this reaction with PCC. PCC is pyridium chlorochromate. You can think of this as like chromic acid light. And what that means is it's going to take an alcohol up a step, up one oxidative step. So a primary alcohol will become an aldehyde, a secondary alcohol will become a ketone. What we have here is a secondary alcohol. So what we will form is a ketone. And we will form that ketone right where that alcohol was attached. Now, the other set of conditions that I have is also an oxidation set of conditions, and this is potassium permanganate. Potassium permanganate is dampened just a little bit by this water, and that is another way to form a ketone. And I'm going to screw that one up, but it's another way to form a ketone with a secondary alcohol. So both of these sets of conditions form the same compound. Now, this compound is called acetyl cyclohexane. This is an acetyl group here. And you can see it looks like acetone. It's an acetyl group. So that's not necessarily going to be on your module quiz for my Organic 1 course, but it may be something that you will need moving forward. So now back to the conditions that are presented in the class, I have this compound, and this is p-toluene sulfonic acid, and it is abbreviated TSOH. Now, TSOH is an acid, and it leads us to dehydration. So we have this dehydration reaction. We're going to focus on beta elimination. So we have a beta hydrogen here, and we have a beta hydrogen here. Now, we are going to follow Zaitsev's rule. So that means we're going to make the most substituted alkene we can when we're going to dehydrate. So this part of the molecule isn't touched. So we're focusing on this part here, what's going to happen. Well, if I take this hydrogen, if I take that hydrogen, I would make this alkene. That's only it's only substituted once. Primary substitution. If I take this hydrogen, then I will form this alkene. That is an internal alkene, and it is di-substituted. It also happens to be in the trans position. All of those things lead towards a more stable product. So now let's name this product. We have to count the longest chain that contains our functional group. So here we have 6. So this is a hexene. Now there is more than one way to name this. I'm going to do it, I guess I'll do it both ways. So this would be 2-hexene, and then we have these 2 functional groups or 2 substituents as well, and they're both at 5. So we would call this 5,5-dimethyl-2-hexene. We could also name this 5,5-dimethyl-hex-2-ene. Either way is acceptable for me. Now with this set of conditions, I'm not sure why we have extra dashes here, but we have sulfuric acid, and it's accentuated, it is acidic. You see we have the hydronium ion. Hydronium ion from chemistry 2 leads us to pH. So here we have a secondary alcohol. We have acidic conditions. We will be dehydrating, and we will follow Zaitsev's rule. Now if I just draw the reactant the way I have it here and take this OH off and make my new pi bond this way towards the rest of the molecule so that I am doubly substituted here, then I have an alkene. Should follow Zaitsev's rule, except it's not in the trans position. The trans position is more stable. Trans, remember from our naming, The trans of an alkene, I kind of goobered that, but the trans is going to be where you have an H on either side of the double bond. This is called the Cis Conformation, and the H's are both on the same side of the double bond. So this will be your minor product, and this will be a major product. Now let's name it. So we have to take the longest carbon chain that contains the functional group. In this case, it is an alkene. I'm going to start my numbering here. 1, 2, 3. And I have a 1-propene. And also on carbon 1, I have a cyclohexyl. So cyclohexyl 1-propene. Again, we can insert that number inside the root. So we could call it 1-cyclohexyl prop 1-ene, all the same. And we have to tell what conformation. So the major product is going to be the trans form. Trans 1-cyclohexyl 1-propene. For the next one, I'm looking at reacting with HCl. Reacting with HCl, I have a secondary alkyl halide. That means I'm going to go SN1. So because it's an SN1 mechanism, I'm going to form both enantiomers. So I need to, and because the reaction is occurring at an asymmetric center, I need to form the enantiomer that retains that stereochemistry and the one that flips the stereochemistry. So now let's name it. We have a cyclohexane that contains both of our substituents. I'll name it up here. And we have a substituent at this carbon and at this carbon. So how do we know which is 1 and which is 2? Well, because all things are equal, and this is one of those cases where all things are equal. This could be 1, or this could be, and this could be 2, or it could be the other way. We have to look to the alphabetical order. So we have an ethyl, and we have a chloro. Because C comes before E, the chlorine is going to get the 1. So this is going to be 1 chloro, 2 ethyl cyclohexane. Now, because we have made the enantiomeric pair, the racemic mixture, we would say that the R and the S version. So you could name them singly, or you could be clear that it is the R and the S. If you put R comma S and then the name, that's not clear. What you're saying is it looks like there's 2 asymmetric centers, and there are, we're only reacting at the 1. So now with this set of conditions here, we have sulfuric acid again, and sulfuric acid is going to dehydrate. We have a secondary alcohol, and we need to look at those beta hydrogens. So let's see, if I take my red, if I'm going to remove this hydrogen, then I will make this alkene, and that is a di-substituted alkene. 2 of the substituents are not hydrogen. Or I could go with 1, 2, 3, 4, this hydrogen, and make this alkene. Then I have a tri-substituted alkene. So because a tri-substituted alkene tends to be a more stable alkene following Zaitsev's rule with dehydration, then that is the product that I should have. So now we need to name it. Naming the longest carbon chain that contains the functional group. This is a cyclohex, and it's going to be at 1-ene. And the reason I'm going to declare it at 1 is because we also have this substituent. So this is 1-ethyl cyclohex 1-ene. Now, usually we are going to define that alkene to be between carbons 1 and 2. So this number 1 is probably redundant, but I'm putting it there just to emphasize the point. With this, we have our p-toluene sulfonic acid that leads us to a dehydration reaction. Again, with Zaitsev's rule and all, This time we only have one beta hydrogen. Here I wrote a B. We only have one beta hydrogen. So this is what gets lopped off with our dehydration. So we will form the product 1, 2, 3, 4. And I went 5. We will form this product. So now we need to name this. Well, we need to name the longest carbon chain that contains our functional groups and substituents that we can name. And we stop here. That's because this is a substituent. It's not 5, it's 4 carbons long. So this is a but-1-ene. This time we definitely need that number. And then on carbon 4, we have cyclopentyl. So this is a 4-cyclopentyl but-1-ene. Now there is no cis or trans to this. And I want to make that clear. And the reason there's no cis or trans to this is because it is terminal and there are 2 H's out here on the end. We don't call this one necessarily cis or trans. We would call this either Z or E. And you would use the CIP priority. It looks like, so we draw a line here. We do have some symmetry but that's not going to be useful. On the bottom side here, this is going to be CIP number 1, and this is going to be CIP number 2, because it's the H that's implied. And on the top, this would be CIP number 1 because it continues, and this would be CIP number 2. So this would be Z for Zwitter, for same. Z, 1-ethyl cyclohexone. I'm not sure I would get that particular until after you've done the last module in my class. So the next set of conditions, we have this thiochloride in pyridine. Well, what does that do for us? Well, what that shows us is we are going to have a substitution reaction, and that substitution reaction occurs out the alcohol. So that is our product. Now to name this product, 1, 2, 3, 4, we have a 1-chloro-4-cyclopentyl butane. And for PBr3, we have a primary alcohol. This is going to be an SN2 mechanism, so that'll be important if you have stereochemistry. And what we're going to do is replace that alcohol group with a bromine. And then we need to name this. Now, I'm going to number this both ways. First, I'm going to go this way, 3, 4, 5. So I have a 1-bromo, 3 and 4 dimethyl. Or I'm going to change my color here. How about purple? Number it underneath. So with the purple, I have a 2,3 dimethyl 5-bromo. Because the 1,3,4 is less than 2,3,5, then I'm going to go with my first set of numbers on top, the red numbers, and go 1,3,4. So my longest carbon chain is 5 carbons long. That means we have a pentane. And then I fill in alphabetical order. So 1-bromo, 3,4 dimethyl pentane. There is no cis trans here, and we weren't given stereochemistry for like this asymmetric center. So we don't have anything to worry about, any stereochemistry to worry about on this one. And for the last example, we have HBr. Now here we have a tertiary alcohol. This is going to react in an SN1 mechanism. If this was an asymmetric center, you would need to draw both enantiomers, but it is not an asymmetric center. So all I need to do is replace the alcohol with a bromine, and then we're going to name it. And I'm going to call this carbon 1, this carbon 2, and this carbon 3. So I have a 2 bromo 1 cyclohexyl propane.